So section 2 is all about work. Work, like we talked about last time, is the transfer of energy to or from a system by the application of forces exerted on the system by the environment. So the environment, remember, is whatever it is that's applying the force. So it could be the hand as you push something, could be whatever that's applying the force. So the work is done by the forces outside the system, referred to as external forces. Internal forces, which would be between objects within the system. So these forces cause energy transformations within the system. They don't change the system total energy, and therefore they do no work. This has to be coming from outside the system in order for work to be being done. So the system must undergo displacement. It has to move in order for mechanical work to be done. So during the time the force is applied, the system has to move in some way. Also, there's a little bit more to that, but for now, that's good enough. So the force of the wind does work on the system in the picture. So we have the little guy in the little sailboat that I can't think of what the actual name is. Windsail? Parasail? No. What is it? Sailboard.
Windsurfing.
Windsurfing on a sail.
No, that's windsurf. That's a windsurfer.
He's a windsurfer. Thank you. So anyway, the wind is pushing, and so therefore work is being done. So the system's kinetic energy increases. The windsurfer speeds up. The force of the wind, F, is doing work on the system. So that's the idea. Assuming there is no friction and initially the windsurfer has no kinetic energy, the wind picks up. The force outside of the system is pushing on the windsurfer, so the kinetic energy is increasing. Therefore, the energy of the system has increased because the work done on the system was due to the force that was outside of the system. Okay? Make sense so far?
Yeah. A question kind of related to yesterday. So we were talking about thermal energy. Can you have it instead of heat, it could be cold thermal energy? So it gets transferred not to heat, but to...
Cold is the absence of heat.
Thanks.
So the thermal energy would go from warm to cold.
There, you can't go from...
You want
Yeah.
cold to go to warm?
No, like can you have cold thermal energy? Like is wind considered thermal energy if it's
warm to cold?
Okay, whatever.
All right, what determines how much work is done? So in the windsurfer, for example, look at that. I just had to wait and I would remember that it was a windsurfer.
They set it up here
It
too.
did
Did it really?
Yeah.
Oh, what? Where is
I
it?
didn't actually read it.
Windsurfer. Oh my gosh. I wasn't reading it, so there you go.
I didn't read it either.
All right, so using the windsurfer example, first note that the longer the wind pushes the surfer, the faster the surfer goes. So the duration of the push makes it speed up more. Also, the more the kinetic energy increases. So that implies a greater transfer of energy. So the larger the displacement, the greater the work done. So there's a delta X involved in work, is what this is implying. Also, if the wind pushes with a stronger force, the surfer speeds up more rapidly, and the change in kinetic energy is greater than with a weaker force. So the stronger the force, the greater the work done. So we have a larger displacement equals greater work. We have stronger force equals greater work. So that means when we're talking about work being done, we must have a delta X involved, and we must have a force involved. So that's going to help us figure out what this equation has to be. And in fact, you can see up here that I have the equation sitting there already. So it's suggesting that the work done is proportional to both the force that's applied and the displacement, d, or we could say delta x. And this is the equation sitting right here. Work equals force times distance that the object, whatever it is, moves. So the unit of work then is the force times the distance, and force is in newtons and distance is in meters. So that means that work is newtons times meters, which is so important, actually, that work has been given its own unit. Instead of writing newtons times meters all the time, we've given work its own unit, and that is called a joule. Joule, joule. So 1 joule is equal to 1 Newton meter. And the joule is the unit of all forms of energy, and it is a scalar quantity. All right, so in this little example, we have the dog in a weight pulling competition pulling a sled 4.9 meters across a snowy track at a constant speed. The force needed to keep the sled moving is 350 newtons. How much work does the dog do, and where does the energy go? So that means we can use the formula work equals force times distance. It's a very straightforward problem. We're told that the force needed to keep the sled moving is 350 newtons. So we have 350 newtons times the dog pulls the sled 4.9 meters. So we simply multiply those two things together.
35 times 5 is.
Yeah, you get 1715 Newton meters, which is a joule. And then we're going to use significant figures, and we get 1700 joules. So the second part where does this energy go?
So it'd be chemical energy, and it gets turned into kinetic energy.
But where does the energy go? So the dog is not accelerating. The dog is running along at probably a constant speed, right? It says right here at a constant speed. So the dog is applying a force, and force equals mass times acceleration. So that force, he's applying an acceleration, right? So, but he's running at a constant speed. So that means he must be losing energy in this system somewhere. So where is that energy going?
Friction.
Yeah, we're losing energy to friction, which is creating some sort of heat. So where is that heat being generated?
On the bottom of the sled.
So what would we call the bottom of the sled?
System.
What are those things on the bottom of the sled?
Skis.
Skis? Runners?
Yeah.
Yeah, something like that. So runners on the sled. What are they doing?
They're causing friction.
So they are not cooling off. They're heating up. Okay, so what kind of energy is this?
Thermal.
This is thermal energy. So we're losing the energy that the dog is creating, or not creating, but the energy that the dog has here in this system, we're losing it to thermal energy. And then it's gone, like we talked about last time, right? Once we lose it to thermal energy, it's gone.
So you're telling me right now?
Yeah, you're losing energy.
So if I do this long enough, I'm going to make the Earth die?
No.
The heat death of the universe.
All right, so work done by forces at an angle to the displacement. So I actually talked about this. I hinted at it earlier. There's more to moving an object, just straight up moving an object. We have to be moving in a certain way. Okay, so if we're at an angle to the displacement, the force on the kite buggy is at an angle to the displacement. So all year long, we've been breaking our motion into components, right? So this force is broken into a horizontal component and a vertical component. So when we look at it like that, the rider is undergoing a displacement in the horizontal direction. We had a perpendicular component and the horizontal component. So which component actually matters is the question. The component of the force that's parallel to the displacement accelerates the rider. The component of the force that's perpendicular to the displacement, right here, only pulls up on the rider. It doesn't accelerate the rider. So therefore, what does it do in terms of work? A force does the greatest possible amount of work on an object when the force points in the same direction as the object's displacement. So less work is done when the force acts at an angle to the displacement. No work is done when the force is applied perpendicular to the displacement. So that means when we have a force at an angle, we need to break that force into components, and only the parallel component will apply work. The perpendicular component will do nothing for work. Okay?
So now if you're moving in the y direction instead, then on the x.
Sure, if we were moving in the y direction, then we would be doing something. But we're not here. We're moving in the x direction. So only the x direction component will be applying something.
Okay, so now what if he comes off the ground? Like,
Well, that would be a different story, right?
well, yeah, but then wouldn't you have, because now he's moving up, but he's also moving in the x direction, so would both of them count?
So that's a different story. Okay, so when the force is applied at an angle, only the component of the force that is parallel to the displacement will do work. Parallel to the displacement, if we're displacing to the right, then the force component that's parallel to that will do work. Okay? Does that answer your question?
You kind of already answered it, but you just won't answer it.
If you have a component that's parallel to the displacement, then that component does work. Okay.
Do you have any problems like the one I'm trying to describe?
All right, so here, calculating the workforce done by a constant force, I mean. So the direction of the force relative to the displacement. So we have the before and after. And last time, remember, I said we were going to be solving problems by still doing the before and after like we were doing with momentum. So here we have the before and after picture. So before on the left, we have the box here. And then we did a displacement. And after is sitting here. Now notice the... which one's the force? The red one is the force. So the force vector was aligned with the displacement vector. We had initial velocity in green and the final velocity here. So the object sped up. We can see that the velocity vector is longer than the final, than the initial. So the angle here was 0. The work equals force times distance. So the sign of the work here in this case is positive. So the force is in the direction of the motion. The block has the greatest positive acceleration. What's K?
Kinetic.
Kinetic energy increases the most. So we have maximum energy transfer into the system in this case because everything is aligned and we're speeding up. So in this case, the second case, we had an angle applied force. Because we're pulling up with this rope. You can kind of see that rope there. We're still speeding up. We have that green initial velocity vector, and then the final velocity vector is longer. We have our displacement still going to the right. But because we had the applied force at an angle, we're losing some of that applied force to the perpendicular component. So the work equals the force times the distance. And then we have this cosine theta involved in there because of the component that had to be found. So the component of the force parallel to the displacement is less than the actual applied force. The block has a smaller positive acceleration. We still have, what's K again? Kinetic energy, but it's increasing less than the original maximum kinetic energy increase. We have energy transfer into the system, but it's not as much as it was before. Now, here, what's going on?
It's being pulled directly up, but it's still having a displacement.
So somehow this box is moving left to right. So it was initially moving to the right. It's still moving to the right.
But it has no acceleration.
We have no acceleration. We have not increased the velocity. That's right. So did we transfer any energy into the system at all?
No.
No. Did we do any work then?
No.
No, because we did not transfer any energy into the system. So there is no work done. No component of force in the direction of motion. The block moves at a constant speed. There is no change in kinetic energy. There is no energy transferred. We have to have a component in the direction of motion in order for there to be work done, in order for there to be energy transferred. Okay, this time we are moving to the right, but we're applying a force in the opposite direction. We have a component in the opposite direction, but it's not fully in the opposite direction. So we have this W equals FD cosine theta. The sign of the work done is going to be negative because we're going to be slowing down the velocity, but it's not maximum slowing it down. We have not quite all of the work possible being done because of the component that's perpendicular there. So the component of the force parallel to the displacement is opposite the motion. The block does slow down. The kinetic energy decreases. The decreased energy transfer out of the system. So we lost some energy there. We're doing work against the direction of motion there. So we're actually losing energy from the system. Okay? And finally, this case, we're completely pulling against the direction of motion. We're not necessarily stopping the object. We just know that we started with an initial velocity and we're finishing with a final velocity. We're pulling straight against the motion here. So we're definitely slowing the thing down in a maximum possible way. We just don't know exactly how much we slowed it down. There is no cosine component here because we pulled directly against the direction of motion. The work done is going to be negative, and this is the greatest deceleration possible. We're maximum decreasing the kinetic energy, and we have the maximum energy transfer out of the system in this case, because there is no component loss in the perpendicular direction.
So does this also apply in angular motion, like circular motion? Like brakes, per se. They're on the rotor, which is moving, but then when you apply the brakes, it's slowing it down at the maximum rate.
Well, I would say that brakes would be a little bit different because of the way that they're applied.
Okay.
Yeah.
Because it's in an angular.
Because of the way that they push out.
The way it's in an angular way too, right?
So, yeah, it's just that that's a totally different idea. Okay, so work done in pulling a suitcase. So we have 120 meters from one gate to another in the airport. It's usually way longer than that, but anyway, you use a strap inclined upward at a 45-degree angle to pull your suitcase through the airport. So it's like one of those ones with the wheels, but not four wheels, so you can just kind of have it at your side. So you got to kind of tug it along behind you. The tension in the strap is 120 newtons. How much work do you do?
Work
Picture.
equals.
Draw a picture before and after. So before, we have our little suitcase. We're pulling it along behind us. Probably there's a wheel.
Just a single wheel.
We have an angle, 45 degrees. What else do we know?
That little tension is 20. We can put in there, can't we?
Oh, sure, tension.
So the force.
Yep. So we have tension is 20 newtons. What else do we know?
Delta X is.
The what?
The delta X is.
Well, I guess D
D?
is 120.
So from here to here, wheel to wheel. 120 meters. Okay. What else do we know?
That's it.
That's all we know?
Mm,
Theta is 45 degrees. Anything else?
and we're looking for work.
Okay. So now what do we do?
Find
Work
our equation.
equals.
Well, I guess choose which one. you use.
So we're going to need a component, right?
Yeah, that's going to be work equals force times the displacement times cosine theta.
Cosine theta?
Except this time, yeah.
Yeah, cosine theta, because tension is the hypotenuse. So cosine theta equals, so that would be tension in the x direction over the hypotenuse. So T sub x equals T cosine theta, right? You guys agree with that?
Mhm.
Okay. So now we can calculate work. So work is force times distance. Our force is T sub x times distance, but T sub x is T cosine theta. So we have T times D cosine theta. We know the tension, 20 newtons. We know the distance, 120 meters.
Cosine theta is.
Cosine and theta is 45 degrees.
I got 1697.06, which can be reduced to
1697.06.
1706.
And then that's newtons times meters, which we know is joules. And then we can call this 1700 joules. There you go.
So instead of
All right. A drag racer is slowed by a parachute. What is the sign of the work done?
Negative,
Negative. Why?
because
He's slowing down.
Slowing down. Doesn't matter which way he's going. He's just slowing down. So the sign is negative.
well, the parachutes.
If we assume that the way he was going was positive,
you're having a force being applied in the opposite direction.
So no matter which way he's going,
Yeah.
let's say he's here. Okay. Which way is he going?
Left
Right.
to the right.
He's going to the right. Okay, so his displacement is this way.
Yes. But he's having a force acting in the opposite direction.
To slow him down, his force is going that way,
Causing the work to be negative.
causing him to slow down, so his velocity is this way, right? And that means over here, his velocity is now like this. So that would cause him to slow down. So the work done then would be negative. By that chart that we were looking at a couple of slides ago, the work done is negative. Okay. What if he was going the other way? So what if he started here and he was actually displacing this way?
Would the parachute go the same way?
How would the parachute go the same way?
Well, it wouldn't. It would hit the car.
Right. So which way is the parachute going
the
now?
opposite way.
So the parachute has to go the opposite way, which means we're applying a force this way.
It's still negative.
So if he's going that way now, his velocity is like this, right?
Well, he had a negative velocity.
Or we could say he had a positive velocity.
We could say whatever we wanted to say, yeah?
Yeah.
Okay. But then now his velocity looks like that.
The work being done is negative.
So based on this, the work has an opposite sign of whichever way it was that we said he was going. So the work has an opposite sign. And really that's what the negative sign is doing, is it's saying it has the opposite sign of whatever sign it was that he had in the first place. So no matter what, the sign is negative. So we can get rid of this question mark here. The sign is negative, meaning it has an opposite direction of whatever direction it had in the first place. Okay? So if several objects act on an object that undergoes a displacement, each one does work on an object. Of course, assuming that we have work actually being done, right? So the total or net work, W total, net work, is the sum of the work done by each force. The total work represents the total energy transfer to the system from the environment if W subtotal is greater than 0, or from the environment if W subtotal is less than 0. So forces that do no work, if the fact that a force acts on an object doesn't mean that a force will do work on the object. So remember, it has to be acting in the parallel direction, right? Otherwise, it doesn't do work. So do we have examples?
Yeah, it should. Forces that do not work.
Good. So we just move along. Here we go. Forces that do no work. What's this guy doing?
Hand clean,
No.
pretty much as a hand clamp.
No, it's not.
But what's he doing is the point.
Weightlifting.
Lifting.
Yes, up. So why is this doing no work?
Because it's straight up.
Because he's not moving with it.
He's not moving, just hanging there, right? So just sitting there, the displacement is 0.
If he was curling it, then he would still be doing no work because it would go back to the original position and the displacement would also be 0.
He's just standing there with the weight over his head. The weight is not moving. Now, he starts moving the weight up and down,
Okay. To get it there, he had a displacement.
but right now he's just struggling. Is his body struggling? Yes. But the weight is not moving. Therefore, no work is being done. The weight is not moving. Okay? A tremendous amount of force is being applied, but the weight is not moving. Therefore, there is no work. Okay?
It's a lot of work to do that.
It is a lot of work to do what he's doing. It's difficult and it's a struggle, yes, but no work is being done.
Dude, I'm gonna think of that next time I'm going to hand clamp. I'm not even doing anything right now. Like,
All right, the holding the briefcase, moving the briefcase. The force that is being applied here is perpendicular to the displacement, okay? This force is perpendicular to the displacement. No work is being done here. Even though we are moving the briefcase, the force that's being applied to move the briefcase is perpendicular to the displacement. Therefore, no work is being done here.
so it's just magically moving itself.
Yes.
Is that,
This
that
is
briefcase
so
looks like
outrageous.
it's heavy.
No, it's not magically moving itself. It is moving. This lady is moving the briefcase, but no work is being done to move it.
This is like so annoying.
You got to think about what work is.
I know, but like there's two definitions to work.
Yes,
Technically.
that's correct. That's why we're going over this.
Oh,
Okay? It is, we are not applying a force this way to push the briefcase. If she were to put the briefcase on the ground and then push the briefcase along the ground, now she's applying work to the system.
Do something, and my parents are like, "What are you doing?" And I pushed a briefcase on the ground. I'm like, "I'm working."
Yeah, that's right. But no, you're not. You're working. She's working, but she's not applying work to the briefcase to move it. Okay? Two different things. Here, what did she do?
She pushed off the wall.
She pushed off the wall. Did the wall move?
No.
Then she did not apply work to the wall.
She applied work
She
to
did
herself.
she did no work on the wall. Okay? The wall did not move.
Oh,
So
well,
if part of the
did-
object on which the force acts undergoes no displacement, no work is done. So she applied a force onto the wall. The wall did not move. No work was done.
But did the wall apply work on her?
A force. So even though the wall pushes on the skater with a normal force and she undergoes a displacement, the wall does no work on her because the point of her on her body on which the normal force acts, which was her hands, undergoes no displacement as that force was applied.
Okay.
Okay? So once her hands left the wall, the force was done. So no work. Okay? So no work was done. So how could energy be transferred as work from an inert stationary object? The energy to get the skater moving comes from her muscles. This is an internal transformation. Chemical energy in her muscles is converted to chemical energy in her motion. While her hand was touching the wall, the force was applied. Her hands left the wall, the force was no longer applied. No work was done.
I love this. This is
Okay?
awesome.
I want to see if you can accelerate acceleration.
All right, which force does the most work?
I think it's C.
See? It's obviously C.
Can we eliminate one of them?
Yeah,
D,
A.
A.
We can eliminate the 10 Newton force immediately.
Which
And D.
then eliminates D.
Correct. We can eliminate D because the 10 Newton force does no work.
And 1/2 of 8 is 4. So.
What do you mean 1/2 of 8 is 4?
Well, okay.
Well, the cosine of 60 is 1/2.
Oh, we're to that point. Finally, we can do that now.
Gabe can.
All right. So we know the cosine of 60 is 1/2.
Yeah.
You guys know that now?
Yeah.
Good.
Yeah.
So this is actually 4 right here. The component in this direction would be cosine 60
4 is less than 6, so.
is 1/2. So 1/2 of 8 is 4, and that's less than 6. So the answer is C. Good. All right. And that's it.